For Meta, I think we're good to start now, right? Okay, can you hear me? Sounds good. Yeah, so Meta, we do augmented reality. So we have made an augmented reality headset. We're on our second generation. And we also do a lot of software with it and provide an SDK for developers. And what I'm going to talk to you about now is how we believe augmented reality can help us improve how we interact with computers. And so how does this happen? Well, this happens through a combination of interaction design grounded in neuroscience. And so I'm in a product management role, so I sit between these interaction designers and these neuroscientists. And I'm going to describe a little bit how that fits together, and in particular, how we can break that down into measurable improvements in how long it takes to learn new tasks, to learn how to do things that are computer-assisted, and how that can also enhance the quality of work. So first, a bit about Meta. We are a startup. We're in Redwood Shores. We're just over 100 people. We have engineers of all types, mechanical engineers, electrical engineers, optics. We have optics people. We have neuroscientists, interaction designers, as I mentioned, and the other types of smart people you'd find in any startups. And we have quite a cast of characters, people coming from about 17 different countries making up our staff. And we were founded in 2012 in New York City, moved to Silicon Valley to participate in Y Combinator. And we launched our first product, the Meta 1, as part of a Kickstarter campaign. We shipped that in 2014, and this is what our baby looked like. So this is unique because it's the first 3D input, 3D output head-mounted display. And if you look closely, you'll see that the display is actually see-through. So you can look and you can see the actual photons coming from the real world, but then you have digital content composited into that, projected in from the side. And this gets into the fundamental problem of augmented reality that we solve, and that is the registration problem, that is bringing together the physical world and the digital world together. And to bring that together, you need, in addition to just a display, you need some way of tracking what's happening in the world. So you notice if you look just above the display, you can see cameras, and in fact, a depth camera. And that depth camera is really the fundamental hardware piece of this interaction technique that we're going to be talking about. And that's being able to reach out and touch digital content with your hands, move it around, and interact with it. But it also has an RGB camera, and that is used to do some tracking of what's happening in the environment. So that was our first generation product, and that sold out. And we got a lot of key learnings on that. We saw the types of applications that people built. People build applications for training people in medicine, for exploring 3D designs of automobiles, for teaching people how to do various remote maintenance sorts of tasks, and of course, gaming and entertainment. And out of this feedback was born the Meta 2. And this is a headset that we launched at TED, on the main stage of TED this year, so just a few months ago. It's available for pre-orders right now, and we're shipping this in Q3. And this is Martin. He's one of our industrial designers. And what you'll notice about Martin is that you can see his eyes. So this is one of probably the only head-mounted display where you can see all the facial expressions of the person wearing it. And as you'll see as I go through this talk, that is really, really important because fundamentally, technology should be connecting people. You shouldn't have a cyborg effect. It shouldn't be creating a barrier between people. And so, some of the things that we improved with the Meta 2 over the Meta 1, the Meta 1 had around a 35-degree field of view. That means you're looking at the world through this little portal. And that's also been a complaint of some of the other recently announced augmented reality see-through display devices. But with the Meta 2, we have increased that field of view to around 90 degrees. And that gives you the field of view that's approaching what you can do on a VR device. And what that means is that you can create an amazingly immersive experience. And that sensor bar that I talked about, that's used to track what's happening in the world, to track your hands, to track things that are in the environment, that's been souped up as well. We brought over some guys from the Google Tango team to help us build a new sensor array that does full 6 degree of freedom positional tracking. And what this means is that with this headset, you can walk into a room you've never been in before, and you can instantly begin anchoring content to the walls and tables and various places. And it tracks you as you move. As I'm moving back and forth now, it also tracks head rotation, and it keeps things very locked into place. And near the end of his TED Talk, our CEO gave us a challenge. And he said that by about this time next year, that all the employees at Meta would get rid of their physical monitors. So we would no longer have monitors on our desk. And you can imagine how crazy this would look in any sort of Silicon Valley office where typically you have a lot of software engineers who have 2 or 3 or more monitors. It would look something like this. It'd like be going back in time to the 1960s when offices, when you had all the space on your desk because you didn't have these monitors, and when you could make this real connection to other people because you didn't have displays creating that barrier between you and them. And I showed a picture like this to my kids, and then I realized, you see that thing on the corner of the desk with the handle on it? They had no idea what a telephone was because they have only ever known mobile phones. And so you can think that in a few short years, the kids are going to look back at the computer monitors on our desk, and they're going to wonder, well, what were those? And so, what might this look like? And how would we interact with it? Well, this will give you a little bit of a taste. So what we're able to do is we're able to take all your applications, your web browsers, your Windows applications, everything you use today, and we're actually able to composite that into the field of view of the augmented reality display. And we're able to track your hands. So as you see here, you can then grab those panels, you can move them around. You can have infinite screen real estate at no marginal cost. And why stick to 2D panels? We can begin to explore and bring it into the 3rd dimension. You can pull that model of a car out of the page and you can stick it on the desk. And that's an amazing way to share information. And I'm going to make just a quick aside at how we filmed this, just so you know that there are no tricks going on here. That was in fact, I don't know how easy it is to see, but there is in fact a camera sticking inside the headset filming through one of the eyes. So that view that you saw on the camera is actually slightly cropped from what you would see through one eye looking through that display. And so this model of interaction opens up a lot of possibilities because there are a lot of situations, a lot of jobs, a lot of sort of things that the current screen-based paradigm of computing doesn't serve very well. Classrooms, for example, haven't really changed much since the 1960s. Kids are still sitting in rows and chairs. Somebody's at a lecture board lecturing and drawing on a whiteboard or a chalkboard. And really, learning can be much more interactive. And so, for example, here's a way in which you can support different types of learnings. You can take something and take it off of the whiteboard, and you can put it into their world. So here's our physics professor, Forrest. He's building our tracking systems. He's able to walk around this model of the brain. He's able to click on it and change it and see the actual neuroactivity in the brain. Now he's just stuck his head inside the brain to see all the neural pathways. And so this is the Glass Brain project from Professor Adam Ghazali at UCSF. And it shows, it's really showing how different parts of the brain pass information. And you would never be able to get that from that whiteboard that you saw at the beginning of that video clip. But for kids to be able to stick their head inside a brain and see what's happening, that, think about that. I mean, that opens up some real possibilities in how we interact and we learn. But yet that's still rather a static experience. That's still about learning and consumption of content. And a lot of what architects and engineers and others have learned to do is to work in 2D mediums, yet imagine 3D. And I spent the early part of my career building CAD/CAM software, and my job was to remove the need for designers to ever need to use clay models in the automotive process. And obviously, we didn't succeed. They still use clay models all the time because they need the texture, they need the 3D, they need to be able to walk around it. And very importantly, they need to interact with other people. And so here are 2 more Meta people, and they are going to collaborate together on an architectural blueprint. They have the blueprint on the desk, and they can pull it, in fact, they can pull it up out of the desk. They can interact with it with their hands. And so what they're seeing as they're reaching out and grabbing with their hands is they have the sense of proprioception. Their visual sense is combined with their sense of reaching out, and they're able to get an understanding of space. Also, remember I talked about the visors being clear. Everything below the brow is see-through. And so they can make eye contact when they're communicating. And so you can imagine if you're in a client relationship and you're an architect and you're pitching a new building or a project to a client, not only can you show a 3D high-resolution image at a fraction of the cost, you can see their facial expression and the reaction on their face when they see it and when they interact with it. But one of the things that I find even the most interesting is being able to see the things that you can't see. You can imagine if somebody is, their senses are impaired in some way. You can then swap in another modality to make up for that. Or even being able to see things that are like outside the visual spectrum, like X-rays or various other things. And our chief scientist, Steve Mann, this is an area that he spends a lot of time in. How do you visualize and see phenomenon? Things that are outside the normal wavelengths, or using various types of time-of-flight sensors to be able to see around walls or even see through walls. Lots of interesting things you can do. And one of the things he does, if you look on the left, is he'll capture a time-lapse image, and then you'll play it back in real time, and you'll get an effect, something like this, through the glasses. Did that play? Hope so. And then if you look over on, I guess it's your right, and Steve talks about something called a darkon. And a darkon is like the anti-photon. And so normally you see light projected through something. Well, what if you could see the absence of light? What if you could see the field of view of a camera? Then you could see something that you otherwise would not be able to. You would be able to observe the act of observing, just like this. And so these are interesting things that you can do with a head-worn display and being able to see these types of phenomenon and enhance our senses, in a way, give us superpowers. But what really makes this better? I mean, we've now shown that we can use computing in areas that you really couldn't use it as naturally for before, and we've created new ways of interacting, but is it more than just another user interface? And I'll make a bit of an intuitive argument. And if you look at how we've evolved processing information using all of our senses, interacting with physical things. So over here on one hand, we got the physical world, but as we introduce language and in the printed word and symbols, then we move into the world of information. But that is information that is disembodied from the physical world. It's information that's on a page. Or 70 years ago, as we got into the computers, it was information that was on a very small, primitive CRT screen. And so the bandwidth between the human brain and that symbolic information was very, very low. And it didn't really take advantage of the capabilities of the human brain. But with being able to, with augmented reality, with the see-through display, being able to combine the whole physical world and overlay information on it, being able to have sensors understanding what's happening in the environment and then showing that information in the context of physical things, we can open up a lot more bandwidth to the brain. We're able to process, just our visual system is able to process 8 to the 10 bits of information per second. That is a massive amount of information. That is a lot more than you've got pixels on a small mobile screen display. And how do we capture that? How do we take advantage of that? How do we create a type of computing that fits well with the brain? And importantly, what does that enable us to do? Well, that's some of what our team is trying to figure out, our team of interaction designers working together with neuroscientists. And what our goal is, it's to understand the degree to which this is, in fact, improving our abilities. So, for example, this simple graph shows an A/B test. And it's an A/B test between traditional computing and being able to have augmented reality supported interactions with a foundation in neuroscience. So this is not a complete work. It's the beginning of a journey for us, but we're already seeing some interesting results. What we're showing here is we're measuring two things. We're measuring the time it takes you to learn how to compute, how to perform some new task. So this could be, how long does it take somebody to learn how to repair something, to assemble something, to learn something? And that's on one axis. But on the other axis, we're looking at what is the improvement in performance. So they're able to maybe learn it more quickly, but are they able to perform it to a higher level of quality? And this is ultimately what we're trying to show. And this is what we believe that augmented reality has the potential to do by opening up a bigger channel of information and fitting more naturally with the way the brain works. We're able to leverage more of our own intellectual horsepower. And as I mentioned, we're just at the early days of this, but we're developing a framework for this. And this is really a framework for interaction and user design that is inspired in and rooted in the neuroscience. I'm neither an interaction designer nor a neuroscientist, but there will be more meta people coming out to explain how this works in detail. But in a nutshell, this is the framework. It starts by being able to tap multiple sense modalities, your sense of proprioception. You know, we're looking at how to integrate in haptics so you get a sense of touch. 11 different depth cues, 4 of which are physiological, the rest are pictorial, combining them together in a way that makes sense and doesn't cause any discomfort. That's the first layer. But then the next layer is what we call touch to see, and that's understanding how our brain integrates these together. So making sure that they're presented in a consistent way that ties into the experience that we're trying to create. And the next is tying into our executive portions of the brain. How does this sensory input trigger us into action? And that's really important when we're not just looking at time to learn, but the quality, reducing the number of mistakes that we make and improving the quality of our work. And of course, all of this happens in a social context. And again, I come back to the fact that our visor has to be clear below the brow so that we can make eye contact, so that we can connect to other people. Because nothing is created nothing of magnitude is created by solo individualists. It's created by teams working and exchanging information. And a lot of the power is really the ability to make these connections and pull this together. So that is the end of my talk, and I've got time for a few questions. Thank you. Any questions? Yes, please.
When you had AR telepresence at kind of like the far right end, kind of like future facing, what do you imagine that looks like? Because if someone else is, you know, say in New York City and we're here, how are you representing them? How are we seeing them through the glasses?
Yeah, that's where bandwidth can become a bit of a challenge. But remember that architect scene where we had 2 different people standing across from one another, the building in the middle? You know, what I would imagine that looks like is we're able to do a 3D capture of somebody in a remote location. And those 3D capture types of sensors are getting better and better. If you just think of like the Intel RealSense, put a couple of those around somebody, maybe a couple Kinects around somebody, and more or less beam them in. And just as, you know, if you're across from me and there's something happening digitally in the space between us, we could place that other person over here and basically map them into that same coordinate system. That's how I imagine it. Anybody else? All right, well, thank you very much. Oh, yeah, one more.
What's your biggest challenge when it comes to gesture control when multiple people are interacting at the same time?
The biggest challenge with gesture control for multiple interactions? Well, there's a mechanical technical problem, and that's that depth sensors often interfere with one another. And so if you get two basically IR-assisted cameras, they can interfere and saturate each other. So that's the first problem. The second problem is, I guess, it will be working out the rules by which somebody has kind of control over the baton, so to speak. The way that we've approached that is to have point clouds of the hands and to support both gestures as well as kind of continuous direct manipulation of the content. In that sense, like I can push it, you can push it, that can all happen dynamically, and it's not really a problem. It fits together quite well. So there are kind of 2 different modalities of hands interaction, gesture-based and then more continuous force-based. The booth at the expo. Well, you want to? What's the? So we have a suite actually, and you see that URL there. So if you're interested in getting a demo of the Meta 2, that is the link you can go to and sign up for it. And I believe that will give you instructions on where to find the suite that we're in. And I believe that there are also not too many slots left. We're getting close to getting booked out for the week. So if you want to see it, sign up now. Yes.
Is there a personal dream AR experience that you hope one of your developers in your community will come up with?
A personal dream AR experience that I would like somebody in the community to come up with? Well, we would like people to create a lot of different apps on our platform. And in terms of like, I would love to see kind of a creation types of experiences where you can create things dynamically, like finger painting in the air, things where you can really interact with all of your senses. So that's maybe a meta answer to your question. Yes?
What do you think the differentiation of this is from something like HoloLens?
Well, okay, so I've tried the HoloLens, and it's, and it's good. I would say one difference is that this has a wider field of view, so that's one clear difference. Another difference with HoloLens is that they've taken a different approach to interaction. With HoloLens, the way you interact is you'll kind of point at something by moving your head, positioning it, and then you'll do this like air tap maneuver. And that's because in HoloLens, they've designed the system for content that's further away, where we've designed the system for content that's primarily within arm's reach, that you're directly interacting with. And so it's really, it has led us to make different decisions in terms of the experience. Okay, well, thank you very much, everyone.